Today, we are going to begin by familiarizing ourselves with a formula that is dependent upon an object's specific heat. We are then going to apply this formula to various scenarios and analyze the effects that specific heat has on heat transfer and temperature change.
So here's what is known as the specific heat formula. It shows that the heat either lost or gained by objects in contact is proportional to their respective masses, temperature changes, and specific heats. Let's try to visualize a scenario where two sodas of similar specific heat capacities are placed in an insulated container. Suppose soda A's initial temperature was measured prior to entering the cooler, while soda B's was not. Given that there is some potential for heat transfer, the two sodas each experience some heat exchange. Upon emerging from the cooler, it is determined that soda A's temperature saw a change of 37.5 Kelvin. Considering all the information we have, we are in a position to determine soda B's temperature change. To determine the temperature change of soda B, let us apply the specific heat formula. First, we must note that due to the conservation of energy, the heat exchange Q is constant between the two sodas. We can determine the heat exchange between the two sodas by utilizing the information that we have about soda A. We can then set the heat exchange equal to the products of the variables that comprise soda B's side of the equation. By dividing the heat exchange by both the mass and specific heat of soda B, we effectively isolate the temperature change experienced by soda B, which is found to be 38.8 Kelvin. Now let us visualize a similar scenario, but with items of much different specific heat capacities. Here we have soda A placed in an insulated container with a bag of chips. Suppose in this case, we measure the initial temperature of the bag of chips, but not of soda A. After the heat transfer occurs, the two items are then removed from the cooler, and the temperature change in the bag of chips is found to be 37.5 Kelvin. Considering the information that this scenario provides us, we can utilize the specific heat formula to determine soda A's temperature change. Again, it is important to note that the heat exchange between the soda and the bag of chips is the same. If we evaluate the equation using the information provided about the variables regarding the bag of chips, we can determine the heat exchange of the system. Since the heat is the same between the two items, we can set it equal to the variables of soda A. By dividing by both the mass and specific heat of soda A, we can determine that the temperature of soda A only saw a change of 8.9 Kelvin. In comparison to the previous scenario, this instance had a greater difference in the two temperature changes experienced by both objects involved in this scenario.
Recall that the definition of specific heat is the amount of energy required to increase the temperature of 1 gram of a substance by 1 Kelvin. Thus, for two objects of different specific heats that experience two independent but equal changes of temperature from 0 to 270 Kelvin, the resultant is each item exhibiting different amounts of energy. Each item's individual potential to either lose or transfer heat is then proportional to their respective specific heats. This concludes our theoretical coverage on specific heat.